Professor had taught at the Galactic Institute of Applied Sciences for 347 years. In that time, she had seen students from 100 different worlds pass through her lecture halls. She had watched civilizations rise and fall. She had seen the slow march of progress carry the galaxy forward, one careful step at a time. But she had never seen anything quite like the humans. The professor stood at the front of her advanced problem-solving seminar, her crystalline body catching the soft blue light of the overhead panels. Her students sat in rows before her. They were like herself, their bodies made of living crystal that sang softly when they moved. There were vast beings of compressed gas who floated in specialized containment fields. There were precise machine minds housed in sleek metal bodies. All of them were the best, and their worlds had to offer. Today, she was going to show them something different. The projection screen behind her flickered to life. On it appeared an image of a crude metal cylinder. It was covered in rivets and welds. Fins stuck out from its base at odd angles. The whole thing looked like it had been hammered together in someone's workshop, which, as new, was exactly what had happened. The students stared at the image. A low hum of confusion rose from the tilted their heads in what might have been disbelief. One of the expanded slightly, a sign of distress among their kind. "What is that?" asked a young named Decimal 9. His voice was smooth and precise, as all voices were. "The design violates 17 established principles of efficient propulsion. The fuel mixture would be unstable. The structural tolerances are far below acceptable standards." "You are correct," said. "By our standards, this device should not work. And yet it did. This is a human rocket from their 20th century. They called it the rocket after the man who built it." The room fell silent. Everyone knew about the humans. They had joined the Galactic Federation only 50 years ago, a young species from a small blue world on the edge of known space. They were crude. They were loud. They built things that broke, and somehow, impossibly, they kept moving forward. "I want you to consider something," continued. "How would you achieve if you had no anti-gravity metals, no quantum computers, less than a century of experience with powered flight?" Silence. "The humans reached their moon using computational power weaker than a child's educational toy," she said. "They did it with controlled explosions. They did it with spacesuits sewn by hand. They did it with mathematics worked out on paper. And they did it in less than 70 years from their first powered flight." A student raised a crystalline hand. "Professor, surely you are not suggesting that their methods are superior to ours?" "I am suggesting," said, "that their methods are different, and that difference has value." She changed the image on the screen. Now it showed a cramped metal capsule, barely large enough for 3 beings to sit inside. Wires and switches covered every surface. There was nothing elegant about it, nothing refined. It looked like what it was, a desperate attempt to survive in the void of space. "This is the Apollo Command Module," she said. "The vehicle that carried humans to their moon and back. It was built with materials we would consider primitive. It relied on systems we would consider unreliable. And yet it worked. Again and again it worked." Decimal 9 leaned forward. His optical sensors were focused intently on the image. "How?" he asked. "How did they manage it?" "Because they had no choice," said. "They could not wait for better materials. They could not wait for better technology. They had a goal, and they found a way to reach it with what they had. This is what humans call creative problem solving." She looked out at her students. Some of them were beginning to understand. Others still looked confused. That was fine. Understanding would come with time. "For this semester," she announced, "your assignment will be different from anything you have done before. Each of you will be given an engineering problem. You must solve it using only the resources that would have been available to a pre-contact human civilization. No anti-gravity, no quantum processing, no exotic materials, just basic physics, basic chemistry, and your own minds." The room erupted in protests. The swirled in agitation. The sang sharp notes of displeasure. Even the usually calm seemed disturbed. "This is impossible," said a student, their voice echoing through their containment field. "We are beings of the gas clouds. We do not understand solid-state engineering." "Then you will learn," said. "The humans had no choice but to work with what they had. Now neither do you." She dismissed the class. As the students filed out, still muttering their complaints, she noticed that Decimal 9 remained behind. The young was still staring at the image of the Apollo capsule. "Professor," he said without looking away from the screen, "I would like to learn more about these humans." Felt something that might have been hope. "Then I suggest you start with the Wright brothers," she said. "They are a good introduction to the human way of thinking." Decimal 9 nodded and left the room, already accessing his data banks to search for information. Watched him go. In her 3 centuries of teaching, she had learned to recognize the spark of true curiosity. The young had it. She turned back to the projection screen and changed the image one more time. Now it showed a photograph of Earth, the small blue world that had produced such strange and remarkable beings. Somewhere down there, humans were still building things, still solving problems, still refusing to accept that anything was impossible. The semester was going to be interesting. Part 2, Thinking Inside a Very Small Box. 8 weeks into the semester, Professor could see that her students were struggling. It was not the kind of struggling she was used to seeing. These were the best minds in the galaxy. They could solve problems that would make lesser beings weep with frustration. But this was different. This was hard in a way they had never experienced before. The problem, she realized, was abundance. Her students had grown up in a galaxy where nearly any material could be found or made. They had access to computers that could run 1 billion calculations in the time it took to blink. They had never known scarcity. They had never known desperation. And so they had never learned to think like humans. Today's class was a review session. Students would present their progress on their assigned problems. Expected disappointment, and she was not wrong. A student named Shimmer of Light was first. Her problem had been simple enough. Design a system to purify water for a small village. She had spent weeks on it. "I have developed a filtration membrane," she said, her crystal body ringing with uncertainty. "It uses quantum tunneling to separate contaminants at the molecular level. The efficiency is 99.9%. "And the materials?" asked. Shimmer of Light hesitated. "The membrane requires synthetic graphene and rare earth catalysts. These would not have been available to pre-contact humans." "Then your solution fails the assignment," said, not unkindly. "You have designed an excellent filter, but you have not solved the problem." Decimal 9 was next. Of all her students, he had shown the most interest in human engineering. He had spent countless hours reading about their history, their technology, their way of thinking. Had high hopes for him. "My problem was also water purification," he said. "I attempted to design a system using only materials available in the human 20th century. He projected his design onto the screen. It was a complex arrangement of chambers and pipes and filters. It looked almost human in its complexity. "The system uses activated charcoal for initial filtration," he explained. "This is followed by an ultraviolet sterilization chamber, then a secondary chemical treatment using chlorine compounds." Studied the design and the power source. Decimal 9 paused. "Solar panels made with cells." "Which would require a manufacturing infrastructure that most pre-contact human communities did not have access to," said. "Your solution is closer than most, but it is still too complex." She could see the frustration in his optical sensors. "Then how did the humans do it?" he asked. "How did they purify water without advanced technology?" Smiled, or at least made the facial adjustment that served the same purpose among her people. She had been waiting for this question. She changed the image on the screen. Now it showed a simple tube, perhaps 30 centimeters long and as thick as a finger. There was nothing special about it. It looked like something a child might make. "This is called a life straw," she said. "It was invented by humans in the early 21st century. It uses hollow fiber membranes to filter water through simple physical exclusion. No power source. No replacement parts needed for years. It costs almost nothing to make." The students stared at the image. Some of them looked confused. Others looked almost offended by its simplicity. "A person puts one end in dirty water and sucks through the other end," continued. "Clean water comes out. That is the entire design." "But that is so simple," said Shimmer of Light. "Surely there must be a better way." "Better by what measure?" asked. "Your quantum membrane is more efficient. Decimal 9 system produces cleaner water, but neither of your designs can be built by a village with no electricity, no factories, and no money. The life straw can. That is what makes it better." A student pulsed with confusion. Why would anyone design this way when superior methods exist? "Because superior methods do not exist if the people who need them cannot access them," said. "This is what humans understand that we do not. They design for scarcity. They design for failure. They design for people who have nothing." She changed the image again. Now the screen showed a photograph of 3 humans in spacesuits, floating in a cramped metal cabin. Their faces were tired and scared. Beside them floated a strange object made of cardboard, plastic bags, and gray tape. "This is from the Apollo 13 mission," she said. "A human spacecraft suffered a catastrophic failure while traveling to their moon. The air filtration system in the lunar module was not compatible with the command module. Carbon dioxide levels were rising. The crew had hours to live." The students were silent now. Even the heads stopped their constant swirling. Engineers on the ground had to design a solution using only the materials available on the spacecraft. Cardboard, plastic bags, tape. They had hours, not days. They talked the astronauts through building the device from 200,000 miles away. And it worked. Decimal 9 spoke quietly. "They saved 3 lives with cardboard and tape." "Yes," said, "this is what I want you to understand. Human engineering is not about finding the optimal solution. It is about finding a solution that works with what you have when you have it for the people who need it. Sometimes that means cardboard and tape. Sometimes that means a plastic tube you suck through. The elegance is in the result, not the method." She looked out at her students. Something had changed in the room. The frustration was still there, but now it was mixed with something else. Curiosity, perhaps, or the beginning of understanding. "I am giving you all an extension on your assignments," she said. "Go back to your problems. Forget everything you know about optimal solutions. Ask yourself instead, what would a human do? What would they build if they had nothing but their hands and their minds and a reason to keep trying?" The class ended. Students filed out, talking quietly among themselves. Decimal 9 stayed behind again, as he often did. "Professor," he said, "I have been reading about human engineering philosophy. I found a phrase that I do not understand." "What phrase?" "2 is 1 and 1 is none." Nodded slowly. "It means that if you have only one of something critical, you effectively have none. Because when it fails, and it will fail, you will have nothing. Humans build redundancy into everything. They assume failure. They plan for it." Decimal 9 processed this for a long moment. "We do not design this way," he said finally. "We design things not to fail." "And when they fail anyway?" They had no answer. He left the room with his processors working harder than they ever had before. Watched him go. The semester was half over. The real learning was just beginning. Part 3. The Examination. The final examination came on a cold morning in the Institute's winter cycle. Professor had spent weeks designing the test. It had to be difficult enough to challenge her students, but not so impossible that they would give up. Most importantly, It had to teach them one final lesson about human engineering. The students filed into the examination hall. They looked different than they had at the start of the semester. They had lost some of their elegant certainty. They moved with a new kind of caution. Even they seemed more grounded, if such a thing were possible for beings made of gas. Stood at the front of the room and activated the main screen. A scenario appeared in bold text. A colony ship is traveling through deep space. 3,000 colonists are aboard, most of them in cryogenic sleep. The ship's primary atmospheric processor has suffered a catastrophic failure. Carbon dioxide levels are rising. Standard replacement parts are not available. The nearest repair station is 6 days away. At current CO2 buildup rates, the awake crew will lose consciousness in 72 hours. Death will follow within 90 hours. Below the scenario was a list of available materials. Spare air filters but the wrong size for the main system, plastic sheeting, basic hand tools, medical tubing, food packaging materials, cleaning supplies, duct tape, lots of duct tape. You have 4 hours, said. Design a solution that will keep the crew alive until they reach the repair station. Remember everything you have learned this semester. Begin. The students went to work, watched them from her desk at the front of the room. She could see the old habits fighting against the new lessons. Some students immediately began designing elegant systems that would never work with the available materials. Others sat frozen, overwhelmed by the constraints. But slowly, something changed. She saw students crossing out their initial designs and starting over. She saw them staring at the list of materials with new eyes. She saw them asking themselves the question she had taught them to ask. What would a human do? The hours passed. Students worked through the night, their bodies running on determination and fear of failure. By the time the examination ended, the room was filled with completed designs. Collected the submissions and began her review. Some solutions were still too complex, too dependent on materials that were not available. These she set aside with a note of encouragement. The students had tried. They simply needed more time to unlearn their old ways of thinking. But other solutions surprised her. A student had designed a simple CO2 scrubbing system using the spare air filters and medical tubing. It was not efficient, but it would work. I had proposed a rotation system that moved crew members between different sections of the ship, spreading out the CO2 load and buying precious hours. It was crude. It was uncomfortable. It would save lives. And then there was decimal 9 solution. Read through it 3 times to make sure she understood it correctly. The young had not designed one system. He had designed 3 different air filtration methods, each using different materials from the list. Each one alone could keep the crew alive. Together, they provided triple redundancy. The first system used the spare filters rigged to a hand-pumped bellows made from plastic sheeting. The second used a chemical reaction between cleaning supplies to absorb CO2. The third was a simple air circulation system that moved the worst air to empty cargo holds, buying time by spreading out the problem. None of the systems were elegant. None of them were efficient, but together they were nearly impossible to defeat. If one system failed, the others would keep working. If 2 systems failed, the third would buy enough time to fix the others. Called decimal 9 to her desk. "Tell me about your design," she said. The optical sensors flickered with something that might have been nervousness. "I know it is not optimal," he said. "By standards, it is wasteful. I have used 3 times the resources necessary." "Why?" Decimal 9 paused. Then he quoted the phrase he had asked about weeks ago. 2 is 1 and 1 is none. If any single system can fail, then all systems must be treated as if they will fail. The only way to ensure survival is to make failure survivable. Felt a warmth spread through her crystalline structure. It was the feeling she got when a student truly understood. "You have learned the most important lesson," she said. "Human engineering is not about preventing failure. It is about surviving failure. about building systems that can take damage and keep working, about never trusting your life to a single point of failure. She marked his examination with the highest score she had ever given. 3 months later, received a message from the Galactic Engineering Council. She read it in her office, surrounded by images of human spacecraft and machines and the 1,000 crude, brilliant things they had built to reach the stars. The message informed her that human design philosophy was being formally added to the standard engineering curriculum across all member worlds. The Council acknowledged, with some embarrassment, that a species they had nearly rejected from Federation membership for technological primitivism had fundamentally changed how the galaxy thought about problem solving. They also informed her that her course had been selected as the model program. Other institutes would be using her materials, her methods, her approach. Human engineering would be taught from one end of the galaxy to the other. Set down the message and looked out her window at the stars. Somewhere out there, on a small blue world, humans were still building things, still solving problems, still refusing to accept that anything was impossible. She wondered what they would think if they knew that their cardboard and tape and refusal to give up had changed an entire galaxy's approach to engineering. She suspected they would shrug and get back to work. That was the human way. A new semester was starting soon. New students were filing into her lecture hall, ready to have their assumptions challenged and their minds opened. Prepared her first presentation. On the screen behind her, she displayed an image. It was a pressure seal made from a deceased crew member's spacesuit and epoxy resin. A human had built it in the desperate hours after a hull breach, using the only materials available. It had held for 6 days. 6 days of life bought with ingenuity and determination and the absolute refusal to die. The students stared at the image. Some looked confused, others looked curious. A few already had that spark in their eyes that told they were ready to learn. She began class with the question she always asked now, the question that had changed everything. "What would you do," she said, "if the elegant solution was not available?" The semester was beginning. The real learning was about to start, and somewhere across the vast distances of space, humanity kept building, kept solving, kept surviving. They always had, they always would. That was what made them human. The end.